Neural networks. Well, it's been a very common words over the past few years. AI, transformers, neural networks, all these type of things. I'm not really that interested in the neural networks, but I am interested in an analog design. And fundamentally, analog is, at its core, more efficient than digital processing. Digital processing is flipping a node from a high voltage to a low voltage. When you do that, it consumes power. And the good thing about digital is incredible noise resilience, though. Analog is troubled by noise, and especially at the low current levels. But I thought anyway that I'd give an introduction to a bit about analog neural networks. So, if you know anything about neural networks and LLMs over the past few years, you will know that there is a paper that came out in, I actually don't know, let's see. Attention is all you need, that's the name of the paper, 2017. And as I understand it, that was sort of the beginning of the transformer craze. What you see in the picture right now is the transformer from that paper. And it consists of a number of neural networks, including feed-forward networks. Now, neural networks, I'd recommend you go have a look at 3Blue1Brown. He has some excellent videos on how to understand neural networks. But they're really a mathematical construct that consists of a number of inputs. In this equation, they are called A. And it's a number of weights. So something you multiply with the inputs, plus maybe a bias, and you take a nonlinear function, for example, a sigmoid or a ReLU or other stuff, and you get an output. Now, as you tune the weights and the biases in these neural networks, you are able to encode, or I should say, able to kind of encode a understanding element into the neural network. Have a look at 3Blue1Brown's videos. They're much better than me at explaining neural networks and how they work. But fundamentally, it's quite interesting with these networks because they consist of fundamental operations. We have addition, there's a plus sign there. And we have multiplication. And for many neurons, so every single, let's look at it like this. If we have a number of inputs, the x's, then we actually have, let's call the number of inputs n. So we have n number of inputs. That might be 12,000 or something like that in ChatGPT 3, which means that our weights will be n squared. So there's a lot of multiplication and addition, because inside matrix multiplication, you take this column vector, you multiply by this row vector, and then you add all the elements, and you're left with one number for that row and column multiplication. And then you add a bias. That's an additional multiplication. And then we have the sigmoid function, and then you're left with a column of numbers. So what you're seeing on the screen now is what is called a fully connected neural network, or fully connected layer, really. A network usually has multiple layers. They can also be not fully connected. And I believe that's what they usually refer to as convolutional neural networks, where you actually take a subset of inputs and subset of weights, and you somehow do the multiplication and summation. But still, fundamentally, it's addition and multiplication that is sort of the key components in any neural network. Yes, there is a nonlinear function, but that's easy. There's only one. So for every single, let's call it a neuron, We have a number of multiplications at the input, and we have maybe a bias and an addition, and then the sigmoid, which means that we get at least n multiplications per neuron. It's n plus 1 if you have a bias, additions per neuron. And I think that if you want to do inference, so now we assume that you've figured out what the weight should be in order to decode whatever you need from the inputs. It might be an image classification or whatever. The use case is not really that important at this point in time. It becomes important. Well, not in this lecture, but at some point, use cases are really important. Problems are important. Where was I going? Yes, there's a bunch of multiplications and a bunch of additions. Now, if you want to do inference efficiently, I think those should be low power. And as I understand, one of the challenges in today's really, really large language models is that you have to shuffle weights in and out of the compute elements because you have to do these multiplications and additions. Today it's done digitally, although it's done in large GPUs and so on. But it's an interesting question. What could we do in the analog domain? So I've been thinking about it a bit, and I've put down a few ways to add quantities and a few ways to multiply quantities. So we can start with the fundamental laws of electronics, Kirchhoff's current law. This is the first thing that you start to learn when you learn electronics, right? You learn how to compute voltages in resistor networks. They may look like the ones on the side here, on the right side. You might have a voltage source and you'll have V1, V2, V3, and then the question is compute V2 given the resistor values, for example. Well, the fundamental equation we start using is that all the voltages in a loop will sum to 0. So if we take V4, or let's start with V1 plus V2 plus V3 plus V4, we get 0. Now some of these will be negative because like V4 will go back up again. But any sort of sum of voltages in the loop is 0. If we then look at capacitors, because on capacitors we can store voltage. So let's say we take 3 different capacitors, C1, C2, C3, and they have their own voltage, V1, V2, V3. We store that voltage on the capacitor, and then using switches, we stack the capacitors. So C3, C2, and C1. This is a very bad C1. Anyway, you can't see the loop here, but if you imagine a loop going from ground up to C3, C2, C1, then the last thing is sort of back to ground. And let's call that V out. Then the output voltage here is really just the sum of the individual voltages. Now, this might not be very practical for neural networks. I don't know. Because there'll be a huge number of capacitors and a huge number of switches. But it's one way to add something. Another way to add quantities is if you have the quantities as currents. Because Kirchhoff's current law tells us that if we sum all the currents in and out of a node, then it's going to equal 0. So any current entering the node must equal all the currents exiting the node. So that's what we say with this equation, which means that if we have a bunch of currents, we can actually just connect a wire together, and the wire will itself sum all the currents. And this can be a very efficient way of summing currents, right? So if we have, let's say we have 1024 currents going in separate wires, and we just connect them all together. Then, hopefully, we'll get a sum of all the currents. And that doesn't really matter if they're positive or negative and so on. It's an efficient way of summing currents, or summing a quantity. Another quite efficient way of summing quantities is using charge, because charge is conserved. So if we again construct a network, that is 3 capacitors, C1, C2, C3, and we store a voltage on each of those capacitors. But what we're looking at now is not really the voltage, but let's look at the charge. So the charge on each of the capacitors will be given by the voltage times the capacitance for the individual capacitors. Now, if we use some switches to reconfigure the network and connect the top plates together, then now we know that the charge in the first period has to equal the charge in the second period, assuming we do the switches right and the transitions between the configurations right. Assuming that we do that right, correct, then charge in the first period, the sum of the charge in the first period, will equal the sum of the charge in the second period. So the Q4 will equal Q1 plus Q2 plus Q3. And now we can compute the voltage at V4, which is going to be C1 times V1, C2 times V2, and so on, divided by the total capacitance. Okay, so these are a few methods that I could think of how we can sum stuff in electronics, in analog electronics. And I think the key, you can do it with op amps and resistors and so on, but that's going to be quite large circuits. As soon as you introduce an op amp in order to force two voltage nodes to be the same or two nodes to be the same voltage, then that's a quite significant increase in complexity. It could be okay if you only have one sum. It might be okay for a neuron. Actually, maybe it's okay. But it adds complexity. So I think also it's good for analog neural networks to look at the simplest possible solutions, because the thing is, with the number of weights and inputs you're going to have, you want stuff to be small. So a second component is multiplication. We want to multiply numbers. Now, if we look at the same configuration, we can notice an interesting thing. And that is that if we just rewrite the V4 a bit, let's call it VO, just output voltage. And then we can see that if it's actually kind of a multiplication that happens here between C1 and V1. Now, the C1 is divided by the total capacitance, though. But if we could change C1, or up to Cn, give it a different value, then we can see that we can add a weighted sum of the different voltages. So imagine that we can actually just say that the W1 coefficient is the C1 divided by C total. Now, if you looked at how, well, basically, we can change this capacitor C1 just by using switches to have less or more capacitors connected as C1. Now, it might be a bit tricky here, since if you scale the W1s independently, then the actual coefficients will depend on the total capacitance. So I'm not sure how that plays into the neural network. I haven't really looked at that, but you can have a look at that and see how it works. So, but one way to implement this multiplication is with digitally controlled capacitance. Another way is mixing. So we can make a current in a transistor by storing a fixed gate source voltage. Now, in this case, the source, this middle of M1, the middle point up here, well, it's most of the time floating. But that means there can't be any current, right? Because the voltage at M1 here, if the M2 is off, is going to be the same as the output. And in that case, in that scenario, there's no current flowing in the output. But as soon as I turn on M2, then the source of M1 is going to be very, very close to ground, and we're going to have a current given by the large signal transconductance times the gate source voltage. And now we could encode our input signal as a period, so or a duration. So we turn on the M2 transistor for a certain duration, and that will give us M1 current times that certain duration. So our output current is now a multiplication between the current in M1 times a duration on the input. Now we have to though go from a whatever input domain we have, voltage, current, whatever, into a time domain. And that's a domain transfer. That's okay. We can do that in circuits, but you need a circuit to do it. But as soon as you have domain transfer here and you have the input in a pulse, then you can get an output current that is a scaled factor of that input. Another beautiful way to multiply numbers is using something called the Translinear Principle. Now, I remember learning about this 20 something years ago, and I found it quite beautiful. I must admit, though, I have never used it. I don't think I've ever used it in a circuit design, but it's still pretty cool. I'm not sure, well, I haven't found any really high class or good papers using the Translinear Principle for multiplication in neural nets, but it's a fun idea. So before we go into that, though, the translinear stuff, realize that when we talk about MOSFETs, they have different operating region. At the lowest level, when we have really low gate voltage, they are operating in a mode that is very similar to bipolar transistors. So where we have an exponential relationship between the gate source voltage at the x-axis here and the current that goes through the transistor. So the relation is roughly given by a zero, or call it a nominal current, scaled by the width divided by length, to the exponential of VGS minus VT divided by the N times the thermal voltage. N in this case is usually about 1.5 or something. And of course the thermal voltage is KT divided by Q. We can rewrite this equation a little bit, and let's just call the scale factor in front of the exponential just an L. And inside that L, most importantly, we'll also hide the threshold voltage, or really the threshold voltage divided by NUT. Okay, the reason I do this is to rearrange the equation a bit to get to the gate source voltage, because that's going to be given by NUT logarithm of the current divided by this L factor. Okay, remember that. Now we look at the circuit. This, as long as you operate the circuit that you're seeing now in weakened version, you can use what's called the Translinear Principle. And it's really a variant of Kirchhoff's voltage law. So remember when we said that the sum of all the currents in a loop, sum of all voltages in a loop must be zero. We can use that to see, okay, if we go up V1, down V2, up V3, down V4, we have a loop and it's back to zero. And the sum of all those voltages must be zero. And we can write it like this. So it's the same as saying V1 plus V2 is equal to V3 plus V4. And now we can use that VGS equation that we had earlier to insert for what that actually means. So we have the NUT, and we have the logarithm of I1 divided by L1, I2 divided by L1, or that should be L2. Let's just fix that. Okay, now it's fixed. So we have the logarithm of I1 divided by L1, logarithm of I2 divided by L1, and that's equal the same on the other side. And now we can rearrange a little bit more, because logarithms are fantastic. If you sum them, like I'm showing here, it's really the same as multiplying the factors within. So I can rewrite my equation as I1 times I2 divided by L1 times L2. And the same on the other side. And now the trick becomes that, well, if the logarithm of these two factors are equal, the factors must be equal. What's inside the parentheses must also be equal. That means I1 times I2 divided by L1 times L2 and so on, those must be equal. And if we assume that all the L's are the same, and that means that the transistors are exactly the same, they're matched, they have the same threshold voltage, they have the same everything, then we can see that I1 times I2 is equal to I3 times I4. And that's interesting. But maybe not that interesting yet. Let's go a little bit further. So let's take that equation and see. Let's take that equation and see what happens when we add an input current and an output current. In this case, I'm renaming. So call I1 just IA. I2, so that's my I2 here. Let's call that IB plus a small current. So something that doesn't really change the operating region of the transistor. I3 is going to be IB, big IB, and then I4 is going to be big IA plus small IA. And if I insert in the equation above, I get what I'm seeing here. I can multiply out, and now I think it gets interesting. So big IA, big IB, and I have the same thing on the other side, big B, big IA, and big IB. I can cancel those two factors, right? And now I'm left with big IA times IB is equal to big IB, small IA. And I can rearrange that. And now I get that the current IB, this small extra current at the, let's call it the output, is a scaled version of the input current, IA. And it's scaled by the difference in the bias currents between those two branches. So if I'm looking at my system here, if I add a small current on one side here, or maybe it was an I4, then everything will arrange such that the current that goes out, for example at I2, is a scaled version of the bias, scaled version of the input. So maybe before we go into a quick demo, remember when I said this L factor is all the same? Well, it's not, right? Because there will always be a mismatch between transistors. So we know that inside the VTH, for example, and actually also inside the ID0, there will be mismatch. But I think most of it is going to be in the VTH, in the threshold voltage. Now that's going to have a certain sigma. And that sigma is usually given by the AVT divided by the square root of the width and length. So that means that the difference between the L's here is going to be proportional to an exponential of AVT divided by the square root of WL divided by NUT. And this might easily be, I don't know, 5-10% or quite a bit. So the trouble with this translinear circuits is going to be mismatch. But let's ignore that for now and look at a demo. So on my GitHub page, I have made a Janeway_SW or SV. It's actually a system Verilog example. I have a different video on that. But inside there, I also played around with translinear circuits. There's a couple of translinear circuits in there. I go through the explanation of how it's done. We're not going to look at the translinear circuit that is shown here, but notice that we have a diff pair at the output. Actually, let's quickly look at the configuration here. So in the picture that I showed you, we have two diode connected NMOS on both sides. In the picture that I'm showing you now, I don't really have diode connected NMOSs. Or PMOSs. I have, was it NMOS or PMOS? That's NMOS. I have NMOSs, but I'm injecting the signal at source. That's pretty much the same thing. Now, the source is going through the gate of two diff pairs. So we can see that if we do a loop again, you can see I can go down from the point. Oh, it's not easy to see my cursor. But down from the point here to the source, and then I go down a voltage, I go up the differential pair, and then I go up a source gate voltage again. And now I'm back to where I started. So this is a translinear loop as long as the MOSFETs are biased in weak inversion. So there's an example of that. But if you clone that repository, which I have done already, it's put it in my ASICs folder, and we open Xscheme. Now I have to remember the name, TBGNV-CTL, I think I called it. And let's see. So here we have a circuit. Okay, let's look at the circuit itself first. So here it's flipped. It's using PMOSes instead of NMOSes, but it's the same thing. The main transistors are 1, 2, 3, 4. Okay, so here we have a translinear loop. If we start at the node here, we go up a gate source, and I go down a gate source, I go up a gate source, and then I go down a gate source. So it's a translinear loop. There's a diode connection here at the top. That's just a set of voltage. And remember when I said you get a scaled version of the bias currents? Or that depends on the bias currents. So IB and IA here now. So IB, that is the current that I put into my diff pair at the middle here. And IA, that's the bias current that flows in these diode connector transistors. So if I inject a current at IP, at IN, then I would expect to see a scaled current at the output. And here we have a test bench. So let's quickly go through that too. So first of all, the SPICE circuit is just listed in the overview here. This is made to run in my ASICs IP type repository. So if you use that, you know how to use it. If you don't, then go have a look at some of my tutorials. And then we have some bias. We need a bias voltage for the NMOS current mirrors, and we need a bias voltage for the PMOS current mirrors. I've chosen to put those outside in the test bench because if we're actually going to use the multiply block here in a neural net, then you would need n number of them, right? And it might be thousands, and you don't want thousand versions of the bias current. It's going to be more inaccurate to distribute voltage across the array, but you probably have to do that. We have a supply voltage that is 1.8 volts, and then I'm forcing the output voltage, the OP and ON, that's forced to be 0.2 volts, and that's so I can measure the current in the output. At the input, well, I get the VBP and VBN, and I have an input current, and right now that input current is 0. So if we run, let's see, we need to use simulation directory. If we run the simulation, and yep, I think that ran, and then annotate the operating points. Okay, first of all, in order to compute the difference between the current in these two, I take a current controlled voltage source and take the current from V1, right, and take the current from V2 and just go plus minus to get the difference. Okay, so that's why I get up here. And we can see that now we input 0 nanoamps and we get about 1 femtoamp out. That's pretty close to 0. And that is what we would expect from our equation. Now let's change this number to maybe 1 nanoamp. Actually, let's go smaller. Let's go 1 femto is a bit low. 100 femto. That's a pretty low current. Simulate. And let's load. Okay. So now I put in 1 femtoamp, and I'm getting out 1 picoamp. Sorry, 100 femto, and I'm getting out 1 pico. So that's a factor of about 10, right? Okay, so if I go inside here, I can notice that for the IB current, I now use 10 transistors. So it's natural that I actually get a factor of about 10. Now, notice it's not exactly 10, because analog, come on, it's going to be inaccuracies in here, especially at these current levels. But you can see that if I control the number of transistors, so a digitally controlled transistor, that's just a transistor and a few, or many transistors and a few switches. Let's assume I reduce it to actually 5 transistors, for example. And go back and simulate. And now I would expect to see around 500 femtoamps. Yeah, so 600. Yeah, close enough. What's interesting is that I can change this number. So let's go picoamp. Now I'm going 1,000 times. 1,000 times bigger input. That's a huge input. That's a huge dynamic range. And you'll see that the output, our output should now be 6 nano. No, 600 nano, right? Yeah. Sorry, 600 pico, so 0.6 nano. So we've increased the input current 1,000 times, and it still works. Now, it's going to work up to, I guess, closer to our bias current. So that's 10 nano at the moment. So let's say I put in 1 nano amp, which means I should get about 6.4 nanoamps out. Let's see if it still works. Yeah, 6.4. Pretty close. So you can see that the multiplication here, around 6.4, stays constant over many orders of magnitude. Unless you run mismatch and then everything falls to bits a bit. But maybe it's possible to do some auto zero. And the reason for this insane dynamic range is the fact that currents and voltages have a huge dynamic range in subthreshold. So that's quite interesting. So I find I don't know if it's going to work with translinear circuits and neural nets. Maybe they're too big, or maybe mismatch becomes so big a problem that it doesn't work. But it's kind of fun to have a look. Yeah. If I were to look at something in analog AI, that's where I'd start. That'd be fun. Might not work though. Okay, I wanted to direct you towards a few other things. So people have actually done analog neural networks, and the place to go is Journal Solid State and IEEE Explorer, and maybe also the International Solid State Circuit Conference. So one paper from Boris Murman and the gang, and I think Marian, what's her name again? Verhelst. Yeah, so if you have access, you can go and have a look at this. They used to do the summation, they used a kind of like a switch cap array. That's quite interesting, like we saw earlier. And then there are people that have been using SRAMs, combination with capacitors. There's people that have been using currents, so scaling, using the weights as currents, and using a time domain for the input, as shown earlier, to control sort of the multiplication of the input and the weight. So it's an interesting area of research. If you have any questions or if you have ideas, then add it in the comments. If you know about other ways to compute multiplication and addition in analog, well, let me know. Thank you. Have a fantastic day.